My name is Julian Munz and I'll be giving the demo of my 345 project for Angluin Learning for the fourth term of 2021. This project entails roughly five functions that we had to implement. The first one being the full function. I'll be giving a rundown of my full implementation and then after that going through the benchmarking of the project. First off, the full function. It's a rather straightforward function. It basically updates all of the table's columns. Whether, say now, close or make consistent had added a new column or row, it would then use membership queries in order to fill up the missing values in the table. For example, if ABA wasn't in ABAA wasn't in the table and hasn't been filled yet, then that's what this function will do. So first it would loop through all the values in S union R, and for each row in S union R it will append each element in the column. It will append each column, and then that's what these three lines do. And then it would check that for if it's in the table already. If it's in the table, it would ignore it because it would already exists over here. And if it doesn't, if it's one of these values, then it will then get this Boolean value member, which does check membership, so it returns either true or false whether temp is in the language or not. And then it adds temp with its membership query into the table, therefore adding it into the column. Then going through my close function, this one's also pretty straightforward, very close to how the theory does it, where it would loop through all the values in R, and for each value in R it will loop for each value in S, and then it would check whether or not the rows, which is this specific the row function gets the specific aspect of the table. And then what it does is it compares it to each R, and if there exists one in R that isn't in S, then it would want to add that specific state into S. So it will loop through and it would find the best one depending on its size. We first declare this variable min, which is set to a rather large number in order to then make sure that the first one is the best R, and therefore after would then keep changing to the minimum sized R. Moving on to the make consistent function. So this function would basically find the best column to add to the table in order to make the table consistent. So the first step was to find all W in S union R such that W is equal to V. What they meant there was where the row of W equals to the row of V, and where W does not equal to V. So therefore we loop through both SUR twice, and we compare each V and W that we named here in this if statement. Inside this if statement will only be where W's and V's rows are equal and where their actual values are not equal. So for example, that will be states such as ABA1 and AA1, where their rows are the same but their actual values are different. Then next step would to be to find all B such that WB and VB are in SUR. So we find then the suffix, we loop through SUR again, and that becomes each one is then R. So we check if W is then a prefix of R. If W is a prefix of R, then we get the suffix, and that would be then B. We append it to W and create a new variable WB and VB. Then what we then do is compare all of the values in SUR once again to see if VB is then inside SUR. Then once we have found VB that is in SUR and WB that is in SUR, and it's abided by all the conditions up until this point, then we find where if WB is not equal to VB for any B, construct the suffix E to be added to the table. So then what we then do is we loop through all of the columns in the, say now, like we would loop through lambda and b, for example, we loop through all of them and we append them to wv and wbe. And then this is basically in order to find which, so we know which row is the same now. We know which row now, or which row is different. So now we'd want to know just which specific column is, it creates the anomaly and where it is the same. So then that's where this function comes in, where it gets WBE and VBE, the specific 1 or 0 value that is different between the two, that makes it the entire row different in this case. And then once we have that, then it's the appending B and E together in order to get the new column to add to the table in order to make it consistent. Once this is finished, then it will call fill once again inside the make cohesive function. So then once it's here closed, once it closes and once it makes consistent, then it will fill once again in order to fill all these columns and rows. Then moving on to the partition function. This one's also pretty straightforward, and it took me a while to figure out what the preds function actually was, but after a while figured out that so the preds function is an array of the different of the boundary values, and these boundary values are then at the specific index is that state. So I have a description here in my report that explains it a bit better. So how my code works for this specific section is if order.size is equal to 1, so this is the evidence that is received from the partition function. If it equals to 1, that means that there's only one specific value to look over the boundary. So it would then get the state of this element, and that state's value would then be order.get0.i, and that'll be on both sides from min to max all the way through for that specific character. So that's why we set preds, if order equals to side, we set preds order.get0i. So this is the state. We set that then equal to the boundary from min to max. Then for the other case where it's bigger than 1, for this example we use 3 pieces of evidence. So this specific part of the function then starts us off, it gets the boundary from the min all the way to order.get i+1.c. This would then be the character just before this evidence piece. So then it would set it to this state. This state would then be all the way from min up until just 1 minus the character at this point. Then from this character it would then be the order.get 0 state once again. So the whole state here would be, so say now this would be state 2, this would be 2 all the way through here up until order.get1.c minus 1, so all the way just before this character. Then from this character it would be the state, let's say order.get1.i is then 0, so then it would be, this would be state 0 all the way through here, and this would be whatever the last one would be up until max. So that this is what the purple part does here. It gets this specific section or this boundary value, and the else basically loops through and keeps on adding or making the boundary value or updating the boundary value depending on how what state we get, and it updates the specific index depending on what state it is. So if it's in state 1 it would update preds 1, or if it's in state 0 it would update preds 0's boundary value, etc. Then onto the binary search querying. This one's also pretty straightforward. It's up here. So I'll explain the low section, and the high section is exactly the same code pretty much, except where it has different initial values. So what it does is I keep track of 4 variables. We have high C, low C, and then low and high. So low and high are the state values. So you get the orderer closest.get0 and closest.get1 are, this would be the smallest value, and then index would be the middle value that is the what was it? It was the counter example that we received from the table, and then they process that counter example, and then that's given in this value and index thing. So this would then be the high values would be the index and the value. The value would then be the character, and then the integer here would be then the state, and it works the same for the low, where the closest.getI would be the initial value that was given to us, and then for the lowest value, and then closest.getI would be the highest value for that. So here we start off the process by first checking if low does not equal to high. If it does equal to high, then that means that we already have the boundaries are fine, and it's already been processed into the table. So if it's not, then it gets this it does ba.get middle between low C and high C, where low C being closest.get0.c and high C being value. So it gets whatever character is in the middle of the two. It sets this old middle equal to null. Don't worry about that yet. That's basically just to end the loop. Then for it would then process the prefix by the specific prefix that was given to us, as well as, and then it appends the mid to that prefix, and then processes it and makes it cohesive in order for it to show up in the table. And then from that, then we are able to get the state of that mid variable that we've just gotten. So now we've got the character and we've got the state. Now we can compare it to whatever low or high state, and then update accordingly. So once we've updated the mid state, then now we can compare it to our low and high. If it's equal to low, that means that the breakpoint is between the mid and the high value. So you set your new low equal to your mid, and then else you set the breakpoint is then between the low and the mid value. So you set your new high value being there, and it loops until your old mid is equal to your new mid. So here we calculate a new mid. All right, so moving on to the benchmarking part of the demo, I'll first be showing how I ran my project using the 2 different methods with different rejexes, and showing the results as well as some of the logging, and then I'll also be showing an overall view of my results that I've received comparing the interval function as well as the BSQ. So first running it using the interval function, we end up getting 4 equivalence queries and 15 membership queries, and it ran in 32 milliseconds. So if we check the tables, it first starts out, every table pretty much starts out the same, and then it keeps adding more columns and more values to it depending on the evidence received. So the evidence received is the same for the first couple using the specific teacher, A, and then B, C, etc. And then it only needs that specifically for this one, for this regex. This regex is rather simple, so we end up getting 15 membership queries and 4 equivalent queries. And then if we were to run it with BSQ, then we would receive quite different results. So then we receive 3 equivalence queries and 105 membership queries, and it took roughly 200 milliseconds. It seems to process quite a lot more using the BSQ. This is due to it trying to find the low and high values and processing each one every single time, processing the new mids, and then this inevitably should lead to less equivalence queries in general. And you'll see that with the general benchmarking. It doesn't show in this one because it's a rather small specific regex, but for example, if we were to run it with ABCA, for example, you would have 5 equivalence queries and 148 membership queries for the interval function. And if we were to run it with the BSQ function, then we would receive 510 membership queries, but only 3 equivalence queries, which is less than before, even though it does run at a slightly higher time. So showing all of my benchmarking that I ran, the time that it took for each for the interval function was a lot faster than the binary search querying, by quite a bit, as well as there was a lot less membership queries using the interval function. I think this might have been because of the specific teacher that I was using for this, and how these specific regexes were more inclined to those ones. I think if we were using more of a random teacher, it would be a little bit better doing BSQ. Then also the equivalence queries ends up being a lot slightly less for the binary search querying. For example, here we get 8, and for the same one we get 12 for the interval function. It can be shown in these tables below that there are considerably more equivalence queries for the interval function, but it's the other way around for the membership queries. So if the system took a lot longer to do equivalence queries than membership queries, but quite a substantial amount longer, then it would be better to use BSQ. But the interval function seems a lot better if equivalence queries and membership queries took the same amount of time. Then it would be a lot better to do the interval function. Time taken also can be shown here, how for each regex, this was the time taken for each one. As you can see, it took a lot longer to do the BSQs with some of the more complicated regexes. But yes, thank you very much.